Hello, this is a presentation of an air heater control system, which also logs data to a database and visualizes it. The requirements for the system was to create a PI controller to control the air heater, uh, perform frequency response and stability analysis for the controller, and tune the PI parameters using the Ziegler-Nichols method. Then, uh, as a real air heater was not available all the time for this project, a simulator was used, which was okay, and the controller should receive data from it and publish parameters to a Modbus TCP server, while also using this Modbus TCP server to get its own controller parameters. Then a general user interface should be set up for the controller with the ability to have multiple controllers logging at once, and also to be able to control the heater set point, the desired temperature. Then, of course, it should log to a database. As your Cosmos database was chosen, and an ASP.NET Core web application should be made for monitoring the data, and this database and web application should be deployed to Microsoft Azure. And here is the system that was made. The air heaters here. One is used here. The system for this was when running the whole thing together. This is quite taxing for the computer I'm using. So there's only one running in this video, but the system is expandable and you can have many more running. The PI controller communicates directly with the air heater. In this case, this is the real air heater. A simulator was used here, but the solution was also tested with a real air heater. Temperature and time is taken from the air heater control system, and a temperature set point is sent to the PI controller to use. This is all via the Pi Modbus server, which we'll come back to. Then time and set point is communicated to and from controller GUI or HMI, and then temperature and time is sent to a database publisher, which also sends it along to the database, and from the database it's extracted from to the Visualiser web app. Yeah, the control system is a PI controller which was created in Python. Stability analysis was performed, and although here, looking at the poles and zeros diagram, there are some poles for some reason on the right side of the zero axis. Still, the Bode diagram and the VC and V100, W100 show that the solution is stable. This control system publishes to Modbus. We will take a look at the control system later. For Modbus TCP, this is an industrial communication protocol which uses coils and holding registers. P Modbus was chosen as this was created in Python, and the server that was used is an example server from P Modbus, which is an async server. This communication protocol has the limits that it only sends integers and has a max cap of the size of 65,535, and it has only 100 holding registers, which means that when sending dates and time and also floating point values, this needs to be mashed into a single string, then turned into a message in bytes and encoded to an integer. Then the integer must be split up into chunks because the integer will become much larger than 65,535, and then sent on each holding register. And the coils, which are Boolean values, are used to register if these holding registers have been updated. And then the receiver can read the registers, and decode the message. The biggest limitation to this is that you can only have 2 heaters per IP address. So if you use an embedded system, you can connect more than two heaters each. Since each holding register, since there are a max cap of 100 holding registers, and each message needs 50 holding registers to be sent. The database, Cosmo DB from Microsoft Azure, is set up and running via Microsoft Azure, and it logs time, temperature, and sensor, and also an ID for each item. The web application, since the developer has very little experience with this was done with ChatGPT, which worked quite well. It gets data from the database, displays it in a graph, updates the graph every minute with the new data from the database, and the user can choose which sensors or all sensors to plot. So we'll take a look at the code. Here is the code for the air heater simulator. There is also the actual air heater communication class down here, which uses a USB 680 DAC, but we will not look at here. These are the assumptions for the simulator, that we have a 22 degrees environment temperature, and that we start at the environment temperature, that the heater gain is 3.5, and we start with 0 control signal. There's a time constant of 23 and a time delay of 3 seconds from the heater has been given a signal to the temperature is actually measured to change. Yeah, and we start time. Sorry, yeah, we start time at 0. Yeah. Okay, the PI controller uses this PI controller algorithm with a proportional gain and a integral time, which are the parameters to be tuned. Then here is the controller. The setup stuff isn't interesting, but yeah, it calculates the error, term error, and then a new signal, and then it limits it to between 0 and 5 volt, since that's the limit of the air heater. This is the heater simulator program, which takes in the heater sim, the PI controller, and the publisher and parameter getter, which are these Modbus classes, which we'll look at after this, and simply runs it in a while true loop until they are interrupted. This is meant to be an actual controller plugged into a real heater, which will just run and send a signal. But for this simulation purposes, this is just a simple Python loop. The Modbus client is the most extensive part of this. There is a template class which has the standard template stuff. Not really needed a connection and update of IP and device number, and this is not even implemented, and then a standard clause. Then right here has an encoding which limits to 600. Yeah, this limit, and also it takes the data, it strings it, then encodes it to UTF-8, makes it into a byte, and then yeah, this makes it into a byte, then this makes it into an int, and then this makes it back into a string. Then it's checked off, and here it's checked. It's written to the registers and updated the coils and handled any problems. For yeah, these prints are just for testing purposes. Then the opposite happens here with the decode. There's added a problem where when you int a string which has a 0 in front, the 0 disappears, but this makes the message unreadable, so there's a fix for that. Then this client is run where it checks the coils to see if they are updated. Then if they are updated, they read the holding registers and output the message. Yeah. Then there is a data publisher, which just reads data published to the server, Modbus server, and sends it to the database. And then Tkinter GUI, which is set up to be to update the plot every minute, those every 5 seconds here, and there is then this is the setup of the function or the GUI. Not very interesting. It runs this check for updates every 5 seconds, which updates plot and checks for updates in temp. Then this plotter is used to update the plot, clears the plot every time, and then redraws it with the new data. Yeah. Then there's a web application here, which this is the function for getting the list of items in the database. Just gets everything with a query. And then there is the code, back code for the main page here, which just sets it up into a chart. All this was done with ChatGPT, but it looks pretty standard, I will think, and outputs it in a JSON. Then a whole bunch of stuff in the Racer page sets up the general HTML, then imports charts.js, which are used for the plots, then yeah, handles updating of the plot and styling, so small styling. Okay, that's that. Then we'll go to here, live demonstration, back to here. Right now it's running, this is the heater simulator, this is the server, and then this is GUI. We run the GUI and it will pop up somewhere here. You can put it over the server, which does nothing. This is just the data used for the plot printed. You can see it here as well. You can change the set point here to say 25 degrees and submit that. And we will see in 3 seconds that this will start changing. Meanwhile, we can publish data by running this data publisher. Just prints what is published. Seems like didn't update. Try again. You see that here that it prints the value it sends. But yeah, so I will discuss this later, but there is a lot of problems with the Modbus TCP stuff, which is why it doesn't update right now. Makes for a very boring graph, but like I can possibly, yeah, you can also change the IP and device number here. We'll do that right now. We can run test.p. This is just something that changes the set point. I've had some more luck with doing this. Just change it once. We'll see if it actually works. Doesn't look like it. Okay, so there are bugs with the Modbus stuff, which is kind of problematic. Okay. Yeah, sorry. We also have the, hopefully this has actually logged stuff. So we have the database here. You can update it and see that we have received some new data points here from right now. Inside one, we can see we have an ID, which is just the time. Then we have a timestamp, temperature, which is just 22 right now. And then simulator was used for sensors, since it's a simulator. And we also have a web application here, which right now shows the simulator sensor, which is just 22. With the test data, we can see it was just some test data I used. And then all sensors, we can see the test data here, and then back down. But yeah, the simulator is what's actually helpful. Then there is a help page here, just short stuff about how this works. And the privacy in the footer, which just says it's owned by me. Okay, back here. So we have seen that there are code for interacting with the read here feature. This should be done in the future, since the simulator is not very useful. There are big protocol limitations and issues with Modbus. I would not recommend using Modbus for this at all. But this, I would recommend something like WebSocket, serial communication, OPC, whatever else. Then expand the GUIs. These GUIs are very simple. You can have possibilities for plotting more than one sensor at a time, and the ability to change more of the parameters for the PI controller, possibility for changing stuff in the web application, not just in the GUI. So that would increase a lot of the security issues, and also possibly login and stuff like that. And running the controller in an embedded system like a Raspberry Pi would be useful. Then you can drop this USB DAC device and just use the pins and pulse width modulation to interact with the air heater. As for security, the system right now stores data, which is not very dangerous, but it could be dangerous because when someone is home, their house will increase the temperature from themselves, and hackers may know when this person is at home and when they're not, and can rob them. They can also use it to change the heater set point to ludicrous amounts, using up all your money, or making your house really cold or really hot. So this controller and Modbus server and the air heater, of course, are meant to be run on a local network, so they're not exposed. Then the data publisher will run or be connected to a Wi-Fi, but it uses a connection string and a key, which is stored as environmental variables, so they are not exposed to say, GitHub, an open GitHub page. And as for SQL injections and stuff related to the database, there is no direct link between the user and SQL stuff. So CosmoDB is not is a non-SQL database. It still uses database language, which are susceptible to SQL injections, but this is not the problem in our case. However, with a future version using a login system, this could be relevant. There are also some GUI bugs, which I forgot to mention, but like you show here, if I now reduce the size of this window, the plot will keep expanding in the vertical direction and will crash the computer. You see here, it reduces, but it goes back if I set it back up and reload it. Yeah. Okay. So to conclude, we've seen that there is a working system, and it can be expanded in future. There are some problems. Modbus specifically is a big problem. Would not recommend using it, but the system works-ish. Well, we couldn't see that it actually worked because of the Modbus problem, but it does at least interact with each other. And if I could have changed the set point, then it would have stabilized around this new set point. Okay, here are the references for the lab, for the heater. I've used Haugen's webpage for the model. Then I've used the Teacher tutorial to develop the Python GUI for the controller. Modbus, I've used this pmodbus page on PP for documentation on that. Then a quick start on SQL stuff for Python to connect to the Cosmo DB, and then an OpenAI chat for developing the web application.